Okay, today we're going to talk about proportions and similar figures, so a little more work on solving proportions, but we're going to set them up today. Learning target is I can write and solve a proportion that models a real-life situation. So, some definitions. Similar figures have the same shape, but not necessarily the same size. Scale drawing. A drawing that is similar to an actual object or place. Scale drawing, like an architect might do for a house. Scale is the ratio of any length on the drawing to actual length. So if you look at a GPS, it usually give you the scale there. Or if you look at maps, look at topographical maps, it'll give you the scale. It might say 1 inch represents 5 miles on the map, something like that. Scale model. A three-dimensional model that is similar to a 3D object. Some of you have built scale models of airplanes and cars and things like that. So if you need to finish writing these down, please just pause the video and finish writing down these definitions. All right, some formulas and properties here. That little symbol right here, squiggly symbol, means is similar to. This little symbol right here means is congruent to or is exactly the same. So similar could mean they're exactly the same, but not necessarily. Congruent means they are exactly the same. Similar could mean one is twice the size of the other or 3 times the size of the other, things like that. There'll be some scale factor, we call it. So here's a little bit of geometry for you. It says finding the length of a side. Finding the length of a side. In the diagram, it says triangle ABC is similar to triangle DEF. Asks what is the length of DE. So it's asking what is DE. So what we're going to do here is looking at these two triangles. You can see that A in the big triangle goes with D in the little one. B in the big corresponds to E in the small, and C in the big corresponds to F in the small. Or color-coded. The green ones go together, the blue ones go together, and the red ones go together here. And so we can set up a proportion that compares a couple of sides. Sometimes what we might do is call, well, here's side DE here. I'll just highlight it in blue here. There's side DE. We're going to call that, we could call it side DE, we could call it X. So we've been solving with X. Let's call it X. So we could say, okay, in this big triangle, 10 corresponds to X. So 10 is to X, as we can see here that the 16 corresponds to the 12. So we can put 16 over 12. Notice that the 18 right here doesn't have a corresponding number in the big triangle. So we're going to use the 16 over 12. And so 10 is to X as 16 is to 12. And now we have a proportion like we had the other day. Let's go ahead and cross multiply to solve the proportion. So 10 times 12 is 120. 16 times X is 16X. And we're going to take out our calculators. Go ahead and divide. So 16X will divide by 16. We'll show that step. 120 divided by 16. So X equals whatever we get when we divide 120 by 16. So let's go ahead and take 120 divided by 16. And I get 7.5. So X equals 7.5. So that's finding the length of a side of a triangle, two similar shapes. So we write a proportion and then solve it. And then you got to ask yourself, does that make sense? I got 7.5 for X. It should be smaller than the 10 that I have over here on the bigger triangle. That seems to make sense. All right. It says the sun's rays, in problem 2, strike the building and the girl at the same angle, forming two similar triangles shown. How tall is the building? Well, we have a ratio of 5 for the girl's height to 3 for the shadow length. So it's height of the girl to shadow length. I have to write that over on the side so we know that we're matching on the next part. Height on the top. So height of the building is x. Shadow length of the building is 15 feet. We don't want to mix those up. That's why we label it over here on the side, height over shadow length. And now we have a proportion. We can cross multiply. 15 times 5 is 75 equals 3x. Divide by 3. We get x equals 25 feet. Look at the picture. Does that make sense over here? That this would be 25 feet. Looks like that would work, and so it makes sense. All right, here's a scale drawing, a map drawing. It says, what is the actual distance from Jacksonville to Orlando? So here's Orlando right here. Here's Jacksonville right here. We've measured it to be about 1.5 inches. You can see on the ruler here. Here's 1 inch right here. There's about 1.5 inches right there. So it says, use the ruler to measure the distance from Jacksonville to Orlando on the map. We have this scale given to us that says 1 is to 110. Let's write over on the side what this represents, inches over miles. 1 is to 110, and so we've measured 1.5 inches over here, so 1.5, we want to make sure we have inches on the top, is to x miles on the map. So we have, once again, a proportion. We cross multiply. 1 times x is x. 110 times 1.5, we do on the calculator. So we have 110 times 1.5 is 165. So 165 miles is the distance from Jacksonville to Orlando. Right. It says more scale drawings. We're going to connect a zip line from the top of the E building down to the flagpole. Using the information on the map to the right, determine how many feet of cable we need. So you'll notice there's a scale down here. It says 1 inch is to 21 feet here. That's a scale model here. So inches over feet. And we see that the zip line, it looks like here in the model, zip line is 25 inches long. So we want to put 25 on the top to go with inches. X on the bottom to tell us the actual feet of the zip line in real life. So we cross multiply. 1 times x is x. 21 times 25 we'll do on the calculator. We get 525. And so that is a zip line of 525 feet. So those are some examples of writing and solving proportions that model real life situations.